All right, AP students, welcome to your AP walkthrough on integrated rate law. So what we have here is we're going to go through one conceptual problem and then two short FRQ. So for a conceptual, what we're given is the decomposition of aqueous sucrose to form the isomers glucose and fructose is a common organic reaction. The following, it involves a strong acid catalyst, and the following balance reaction is as written. The following data was then collected in lab. So complete the data table. So remember with integrated rate law, what we do that's unique about it and why it's so useful is that we do a derivation via calculus that allows us to now compare concentration versus time. Okay. And that's particularly useful to us, right? Regular rate law compares concentration versus rate. But in the end, what we really need to know is how much can I make in a certain amount of time? And the rate relates those two things, but I want to know them individually compared to one another. So we have a couple general categories that the relationship between a reactant's concentration and the time it takes to produce it. And that is first, second, and zero order. And if you guys remember or know anything about calculus, you know that anytime you derive something, it's always one power kind of less or one. Yeah, it's kind of normal for us to shift down, right? I don't know. Yeah, like a squared becomes a single power, right? If you guys are at all familiar with like calculus, like a parabola becomes a line and a line becomes a parabola becomes like a diagonal, and then a diagonal will become like a line, if you guys know anything about calculus derivations. So the same pattern is mimicked here. So what we are given is we're given time, and we're given the concentration, the original concentration in molarity measured of the sucrose. And then what we do is we plug the value of the sucrose concentration into the calculator and perform the following calculations, which is natural log in your calculator of the given concentration and 1 over the concentration. And the reason why is that each one represents, okay, first versus second versus zero order. So the relationship between time and concentration plane is examining whether we have a zero order. The relationship between time and natural log helps us identify if we have a first order. And the relationship between time and 1 over the concentration helps us analyze if we have a second order. So when we plug in these values into the calculator, what we get is minus 1.15, minus 1.33, minus 1.44, minus 1.66, and minus 1.92. And we get, for 1 over the original values, we get minus 0.868, minus 0.751, minus 0.697, minus 0.602, and minus 0.520. And what you're asked to do is to plot generally the shape that would be connected with this. So I'm not going to like analyze it hardcore, but what you should kind of get is a curve for this. You should get a downward slope for this. And you should get, oh, do it. No, you shouldn't get a downward slope. You should get an upward slope. As time progresses, it becomes, no, downward, because it becomes more and more negative. And then you should get a slightly upward slope. Oh, good Lord. Slightly upward slope for this. I'm not going to be a stickler about your graphing skills today. That's not really the important part here. Okay. On the AP, it tends to give you the graph. And so what you say to yourself is, well, based off of the relationship graphically between the values determined and the time, what we would say is that the plotted graph shows that our reaction is indeed first order. It is a first order relationship or reaction between, okay, the concentration and the rate of production and time, because what we see is a linear relationship. And whenever you see a linear relationship, that identifies the order, the integrated order that we are addressing. Okay, so then what would our rate law expression be in the general form? Well, rate law is equal to some constant K times the concentration of your reactant. So our reactant is, we only have a single reactant, glucose, which is C12H22, or is it glucose? No, sorry, sucrose. C12H22O11 raised to what order? What power? 1. And so we don't write that in that one, and that's it. Okay. So then write the expression, determine the rate constant, and include the units for the rate constant. So then what we would say is, for the units of the rate constant, we would manipulate the equation and say that, well, it's rate divided by, okay, concentration, C12H22O11. And by the way, the rate value would be molarity per second all over molarity. So what would our rate constant units be? Well, that would make it a unit of seconds to the -1, or 1 over seconds. Now, if we determine the half-life, given that K is equal to 0.0046 S to the -1. So half-life is a very special type of integrated first order, okay, reaction. And what you would want to look on is the AP equation sheet. And it gives us a direct formula for calculating, okay, half-life, or for calculating the amount of concentration left, or so forth, given half-life. And that is T half, which is a symbol for half-life, the time of half-life, the time it takes for half the sample to decay, is equal to 0.693 all over your rate constant. So we would say then this is equal to 0.693 all over the given rate constant of 0.0046 seconds to the -1. And that would mean that our half-life time is indeed, just do the math, 151 seconds. And we do tend to report in seconds. Okay, 151, and I'm just going to write seconds with an S. Okay, 151 seconds. All right. So E, if we performed a new trial with an initial concentration of sucrose being 0.400 molarity, what concentration would remain after 4 hours have passed? Okay, so something to keep in mind is, if we look at this, what we get is, on the AP equation sheet, we get a relationship, a linear relationship that is tied to every integrated rate law order. So first, second, and 0. And we get, for our first order equation, because we're dealing with a first order integrated equation, we get the following AP equation sheet: ln, natural log of the concentration of whatever compound we're talking about, okay, final, okay, minus ln of the concentration initial, okay, equals -K times T, the time that you are reacting. And so what we would do then is, one, we would want to plug in our data. So right now, what we have for data is that we have, and we're trying to find the initial, we're trying to find the final concentration. So we're trying to solve for ln of A, and I forgot to put little final. So what I would do is I rearrange my equation. I'd say ln natural log of my compound, okay, is equal to -KT plus ln of the original concentration of my compound. And so now that I've rearranged to solve and isolate for my variable, now I'm going to plug in what I know. So I know that K, all right, -K is 0.004 seconds over 1 times the time. Well, I'm given it in 4 hours. So if I do unit conversion, 4 hours is equal to 14,400 seconds. And I'm assuming you can do unit conversions at this point. So 14,400 seconds time plus, okay, plus, and I'm sorry, I'm going down below, plus ln of my starting concentration, which was in the problem prompt 400 molarity. Okay. And I don't have to bracket it now because it's actually a math equation. So now I'm going to put parentheses around it. And what you would get then is that the ln, oh man, I don't know why I'm drawing all these lines in. What in the world is happening over here? The ln times the concentration of our final amount of sucrose is going to be equal to negative 67.15629 and so on. It's excess numbers. So then we're going to take the anti-log of this to solve for actual concentration of A, because that's what we're actually being told, the final concentration of our sucrose. And I'm just keeping A in for right now because I don't want to write out everything. And that's going to be E raised to the negative 67.15629 anti-natural log. And we would get then that the concentration to the correct sig figs of our sucrose after 4 hours is going to be 6.8 times 10 to the negative 30 molarity. All right. So there's your answer. There's your walkthrough. Let's go ahead and head to an AP question. So we're going to do AP question number 1 and 2. So we're given for 1, we're given the following structure of cis versus trans. By the way, a cis molecule means it has 2 distinct terminal types where they're on the same side, cis, and trans means that they're on opposite sides. Okay. But they're composed of the same type of terminal groups. All right. So we have been told that the half-life, T half of the catalyzed isomerization of cis-butene to produce trans-butene is represented above, and it was measured at various conditions, giving us the following values. Okay, you see pressure, volume, and temperature given as a value. Just FYI, that should make you think automatically of Unit 3 ideal gas law. So you know you're probably going to be part of the FRQ is going to be integrating Unit 3 ideal gas law equations, just as a little pointer. So we're asked A, the reaction is first order. Okay, duh. Explain how the data in the table is consistent with the first order reaction. So we know that a first order reaction, okay, should have as well, we could think about 2 ways. Okay, we could think about it as first order reactions. If I double the concentration, if I double the concentration of, let's say, butene, then I should get double the rate. But here's the problem. That's not a great way to think about it in this context because of the fact that we're not given rate values or time to figure out the rate, but we are given half-life. So what we see is that for the first order reaction, the half-life is actually independent of the reactant concentration. All right. So what we see here, and honestly, this is maybe a particular FRQ portion that I'm actually just teaching you through the problem instead of addressing in class because it's such a nitpicky type of AP question where might be just something where you kind of make a note to yourself, note to self, this type of question might come up. Okay. Where it's keep in mind where this would be the normal way of understanding first order. What we have is first order in the context of a half-life reaction. So what we are going to draw is the following relationship for a first order reaction. And this is start the part that you might just want to memorize. Half-life, okay, is independent of concentration. As we see in trials 1, 2, and 3, right? It remains unchanging. The half-life remains unchanging between trials 1, 2, and 3. So calculate the rate constant K for the reaction at 350 Kelvin, include appropriate units with it. So this is, again, where we go back to the AP equation, where in terms of half-life, we don't really have any other information to calculate the constant. We don't have any data of change of pressure. We don't have any of that. We don't have, well, we do have change in pressure. We don't have change in rate. So we can't do the stereotypical first way I introduced to you with rate law data from initial rate, initial pressure. We can't do that here. So instead, we're going to take advantage of this half-life, and we're going to use our AP equation sheet and say, well, I know that T half is equal to, for a first order half-life equation, 0.693 all over K. So I just rearrange this to now have K be isolated and say that 0.693 is equal to the half-life divided, 0.693 divided by the half-life is equal to K. And so what I get is 0.693 divided by 100 seconds and 3 sig figs. And I get that the K value is, is equal to 0.00693 seconds over 1 over seconds, or hertz, or no, that's, I guess that's that's a physics way of thinking about it. Oftentimes for these problems, by the way, half-life problems, they do give you a point for including units, kind of just as a thing that they do. So C, is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? And what we would say is, looking at trial 1 and trial 2, we see that trial 1 has 300 torr, just a value of pressure, and trial 2 has 600 torr. So what we would say then is, according to a first order reaction, right? According to a first order reaction, we're just going to copy this on down here. Okay, according to a first order reaction, oops, I got too much of something. Oops, hold on. Let me try to get this, just this. We know that if I double the concentration or change the concentration, it should double the rate. So between trial 1 and trial 2, the initial rate for trial 1 is greater than the initial rate for trial 2, because concentration is doubled, or pressure is doubled, which is an indicator of concentration. Because pressure doubles, all right. Sorry, did I say initial rate for trial 1 is greater than? Sorry, I meant less than. Hold on. Less than. Wow, what a brain fart. Less than the initial rate for trial 2, because pressure doubles in trial 2 and is directly, okay, correlated to rate, right? In first order reaction. So trial 1 is less than trial 2 pressure wise, which means its rate, trial 1 rate, is going to be less than trial 2 rate, according to first order reaction principles, right? Is directly correlated to rate in accordance to first order reactions. Sorry, that went over. So D, the half-life of the reaction in trial 4 is less than the half-life in trial 1. Explain why in terms of energy. So why do we see the opposite happen? Or why do we see, trial 4 is less than. Okay, so why are we seeing the sudden change in our data that we go from half-life 100 to half-life 50 between trials 1 and 4? So what we see here is that obviously something about the mechanism of the actual decomposition is changing. So we know that the greater the energy barrier, the greater the activation energy, the less successful collisions that meet that activation energy, the less product, the less rate of successful reaction. So what we see here is that for trial 4, okay, we see that trial 4 is occurring at a temperature of 365. Trial 4 occurs at 365 Kelvin, which is greater than trial 1 occurring at 350 Kelvin, right? Which means trial 4 conditions results in more kinetic energy and therefore, and thus more percent of particles that meet activation energy. Okay, so you can kind of go from both ways. All right. You could flip it and say trial 1 is occurring in less temperature, which means particles are moving slower, therefore less are meeting the activation energy. Either way, the relationship, as long as it's true, will be accepted. Okay, so now let's look at question 2, short FRQ. What we have is we have blue food coloring is oxidized by household bleach. Remember, oxidize means lose electrons. Okay, which contains OCl. Anyway, to form colorless products as represented in the equation above. Where is my equation? Oh, yeah, that equation is so funky. It's Na2C37H334 N22. Whoa, N2S3O9. Okay, that was a really funky way of writing it. A student uses a spectrophotometer set at a wavelength of 635. So that must be max wavelength. And remember, at lambda max, there's 100% absorbance. Okay, at lambda max. To study the absorbance of the food coloring over time during the bleaching process. So this is connecting to the idea that we can measure concentration through other means, where we can take the color and put it into a spectrophotometer as an indicator of calculating concentration and therefore rate of production or consuming. All right. And so use the data below to answer the following question. So based on the graph above, what is the order of the reaction with respect to the blue food coloring? Well, we know that if you have an ln and ln versus time, and that's linear. So anytime you get a linear relationship, you know that reveals the order. Linear tells you the order of reaction. So ln versus time being linear tells me this is a first order reaction. And I don't know why my TAs, when they made this, with so much space for that question. So the reaction is known to be first order with respect to, wow, I love how they just tell you in the next part. In the second experiment, the student prepares solutions of food coloring and bleach with concentrations that differ from those used in the first experiment. When the solutions are combined, the student observes that the reaction mixture reaches an absorbance near 0 too rapidly. Okay, so that means it basically becomes transparent too fast. There becomes not enough production. Okay, so in order to correct the problem, the student proposes the following possible modifications. Circle the one proposed modification that could correct the problem and explain how modification increases the time for the reaction mixture to reach an absorbance. So how do we slow down that process of creating product, which is going to create a colorless solution? Or sorry, how do we slow down the process of consuming reactant? So here we're trying to slow down consuming reactants. So what we need to do is, if we increase the temperature, it actually speeds up the reaction rate. So we don't want that. And if we increase the concentration of the bleach, that does not help us because that would increase the reaction rate. So what we instead want to do is increase the concentration of the food coloring itself so we can catch the production. We can have a more accurate account for all particles. So what we say is that how to explain this is that the initial concentration of the blue food coloring, so by increasing initial concentration of blue coloring, food coloring. Sorry, guys, I'm getting a little lazy on writing. It requires more time is required. Okay. And this, yeah, that's basically it. More time is required. And here's why. Because regardless of the reaction order, For the bleach to oxidize, you according to the prompt, you need blue food coloring. So you just have more time needed. Okay. So C, in another experiment, a student wishes to study the oxidation of red food coloring with bleach. How would the student need to modify the original experiment to determine the order of the reaction with respect to red food coloring? So what you'd have to realize, if you're changing color, you have a change in color. That means you're going to have a change in absorbance patterns, right? You're going to have change in absorbance patterns. So what you're going to need to do is you're going to need to change or reset the lambda max wavelength. All right, so that your spectrophotometer is set to account for the red color absorption and transmission. So that's all I have for you today. Good luck and great job, you guys.